So the first section we're going to be covering physical and logical access to assets. This is about making sure only authorized people or systems can use or get access to resources. Could be a physical resource like a server room. It could be logical like a database. But these are things that we do to protect tangible assets. Buildings, server rooms, data centers, laptops, physical access controls, right? What would that include in general? It would include things like physical barriers, fences, gates, bollards, security guards, man traps, turnstiles, doors with locks on them, internal security things like server racks that might be secured or a safe. It also includes identification and authentication like badges and ID cards, smart cards with chips or RFID readers on them, right? Or RFID transceivers, right? Biometrics, fingerprints, iris scan, facial recognition, security guards that act as a secondary or compensating control if for some reason primary controls are not sufficient. We also have detection and monitoring components. Cameras, motion detectors, sensors, alarms, intrusion detection systems for physical access. And then we have environmental and safety as well. Fire suppression, HVAC, temperature sensors, power protection like backup generators, UPSs, and so on. So there's quite a bit that we're going to talk about in this section. Let's start with physical and logical access to assets. So here we're talking about applications that deal with financial, privacy, safety, defense. This is going to include some form of control. Remember, access control is a foundational concept, right? Especially when we're talking about securing systems. If we have sensitive domains like financial sector, privacy concerns, safety concerns, defense concerns, we need to be able to govern what legitimate users are allowed to do and block unauthorized attempts to access those resources. This is going to involve the use of authentication, which is the process of verifying somebody's identity, and authorization, which allows us to define what each of those individuals are going to be permitted to do. All right? Now, these structures that we implement, these authorization structures, they're going to be representative of the organization's hierarchy, which is going to be based on the sensitivity of what it is that we're trying to protect, whether it be documents or resources, and the need to know or the clearance level of the individual users. They could be physical access controls like key card readers. They could be logical controls like login credentials. Oftentimes, you'll see kind of a combination of these things. And when we're implementing them, we have to be careful to consider who's going to use them, how are they going to be used, so that we can make sure that we have functionality, right, to authenticate and authorize, but also have protection, right? So what are we trying to protect, right? Maybe it's sensitive applications. It could be systems in a finance or defense environment that need strict access control to protect critical data and operations. It could be what is the purpose of access control, right? Purpose of access control is going to define which legitimate users can access information and what can they do, which is going to prevent unauthorized access attempts. Think of it like a gatekeeper between users and resources. We need to understand the concept between authentication and authorization. We've talked about that in the previous domains. Authentication verifies your identity. Authorization defines what actions you are allowed to perform, right? Then we have authorization models as well. These can be things like role-based access control that kind of is organized based on the structure of the organization. It could be clearance-based, meaning that what is the sensitivity of the information that an individual is accessing and what's the user's clearance level. It could be different types of access control systems as well. Physical systems like locks, badges we talked about, or electronic or logical systems like software permissions. And those, by the way, are going to pretty much work together to enforce access rules, right? And then we have the integration of systems. Both the physical and logical controls get combined together, right? So you might swipe your badge to access a data center, but that's also going to create a log entry indicating that somebody has accessed that data center. And then we also have installation considerations. Who's going to use the system? How is it going to be used? Is it effective, right? Is that particular method effective? Is it convenient? Convenience is not always the biggest concern, but it does have to be usable. Is it user-friendly? That kind of thing. All right. All right. All right. Physical and logical access to assets. Access control systems obviously are going to vary, right? It depends on the size of the organization, how the organization is operating. A bank is going to have pretty advanced systems because they don't want public access to the safe or restricted access to the ATMs. But a small business might have a shared key that everybody uses to get access to the break room or to the office itself. These facility access controls don't just protect our assets, but we also generate logs on who accessed what and when. Why? Because we want to have an audit trail. So most modern systems kind of bring all of these things together, right? We've got physical access, we have time tracking, we have logical access with credentials. All of these things together provide for streamlined security, right? Usability is absolutely critical. Logical access control mechanisms almost always are software-based mechanisms, meaning that we're going to limit user access to data and system functions based on what? Based on their role or their need to know, which could be a result of some sort of clearance level. These controls usually get embedded into an operating system, right? It could be embedded into the application's logic, like if you look at a database system, for example. But you could also incorporate the use of external security packages as well. In some cases, we even manage these controls with completely separate systems that will either work over communication networks or some, external communication channel. All right? So going back to the concept of the small business and the bank, right? A bank will have layered access controls, right? To protect different security zones. A small business would maybe have less granular controls, right? As far as facility access control, we need to have systems that protect physical access, that maintain logs of who accessed what and when. This is going to be absolutely critical for things like audits and if you're dealing with incident response, right? In some of our previous domains, we talked about disaster recovery plans, incident response plans, and so on. All right, we'll see more of that in this section as well. Unified credentials is a consideration as well. You have a single credential like a smart card or maybe biometric login, which can be used for all of these things: physical access, time tracking, system login. This is going to reduce the complexity of the system, but it will also improve overall security. All right. Let's see what else here. Oh, implementation layers, right? Meaning that logical controls could be built in. This is the second to last bullet point. Built into the operating system, right? Where you have file permissions. It could be embedded into the application, right? A database management system access rule could be built into like a database. It could be added with external security components as well, like endpoint protection software. Maybe we implement an EDR solution on our desktops for endpoint detection and response. It could be managed by separate systems that communicate, like a firewall or identity federation systems, right? So again, it's quite robust, right? We see a lot of pieces. Okay, so what are the different access modes? I think this is pretty self-explanatory, right? The goal of logical access controls is to permit or deny access by specific individuals to specific information resources in specific access modes. All right. So the purpose of logical access controls is a way for us to define who can access what information in which mode. It could be viewing, it could be editing, it could be executing, right? Those are the three options that we see here. These modes essentially determine the level of interaction a user can have with a resource. And I think it's pretty self-explanatory, right? Read-only means users can view, they could possibly copy or print data, but they can't modify the data. Read-write access means that users not only have the read-only access to view and print, but they can also edit, they can delete, they can alter the data. Execute means that we can run applications, we can run programs. We don't need to read or modify the code. Obviously, most users probably won't even understand how to do that anyway. Developers, they might get read and write access, especially if it's code that they're working on. All right. Access modes can also be time-bound, or they could even be version specific, meaning that users might have read-only rights to one version of a document, but they could write to, say, another document. All right? So, read-only, view, copy, print, cannot change. Read or write, full access to view, modify, delete, or update data. Right? This could be like editing spreadsheets or managing content on a website or updating records. Execute, you can run applications, but you cannot read or alter the actual application code, which means you can maybe launch an application, you can run different scripts, you could access compiled programs, but you can't modify compiled programs, right? And then we have conditional access, meaning access can vary based on time, based on context, based on the content. All right. If I tie this into a real world example, let's say we're thinking of like AWS as a cloud solution, right? We can do enforce identity and access management policies where you could get objects in AWS, but you cannot put objects. That would be an example of read-only. All right. Execute could be tied to something like Lambda functions, where you can trigger executions, but you can't modify the code. Whereas developers could have full access to EC2 instances, which would be like code repositories, stuff like that. End users can only interact with the application. Does that make sense? All right. Centralized, decentralized versus hybrid. Administration of logical access controls involves implementing, monitoring, modifying, testing, or terminating user access on a system, right? Those are the tasks, right? We need to be able to configure permissions. We need to be able to monitor for usage. We have to have logging activities, and we need to be able to continually review access controls. Decisions about who should have access and what kind of access is controlled by one individual, the data owner, not the system administrator. Right? We talked about that in one of our previous domains when we were talking about the data custodian, the data user, the data owner, etc., etc. All right. So the decisions would be guided by policies in the organization, would be guided by things like job roles. We have a principle of need to know, right? Which we talked about previously, and I think you guys understand that concept, right? To manage access in an efficient manner, we have three different options. We have centralized administration, decentralized administration, and hybrid administration, right? So we'll break down centralized first, right? A single person or a single authority configures and manages the access controls. Now, why is this a positive approach? Well, because it makes sure that we have strict oversight. It's easier to revoke access if somebody leaves the organization. All right? If you talk about decentralized administration, this means that you're going to have different departments or different units within the organization that are going to manage access independently. This gives us a lot more flexibility, but it absolutely requires much more significant coordination. All right? It says here, access to information is controlled by owners or creators of files, whoever or wherever those individuals might be. Right? Why would it require coordination? Well, it's going to require coordination because now we have multiple individuals that are responsible for handling this access control. And you know the old adage, right? Your chain is as strong as the weakest link, right? So why would we choose to use this particular model? A lot of times, those individuals in those departments, in those organizations, in those kind of subdivisions, if you will, they're the ones that generally will have a better understanding of who should have access, what level of interactions those individuals should have with that information, and we're controlling access closest to the data. Does that make sense? So, but it does introduce a lot of challenges. There can be inconsistencies on how access is granted by different individuals. Different individuals might have different perspectives, right? There can be a lack of visibility into overall system-wide access. You could have conflicting permissions, which ultimately would result in security gaps. There could potentially be ethical concerns as well. And it can also be difficult to revoke access. If an employee leaves, now we might have multiple individuals that are going to be responsible for managing that individual leaving, right? So because of these specific issues, a lot of organizations will develop a hybrid model. Some data is governed centrally, depending on the criticality of that information. Other data might be managed locally. That's going to give us a nice balance of control and flexibility, right? So going back to that previous example, the AWS example in a multi-cloud enterprise in this case, decentralized would mean that in this example, development teams would manage access to their own AWS buckets or their own AWS subscriptions. In a hybrid model, the security team would centrally manage any kind of identity and access management to sensitive systems like financial systems or HR systems, but then the product teams will handle access to their own environment with their own policy constraints. Does that make sense? So a lot of organizations develop that hybrid model. Okay? Accessibility of space, physical access control, right? Being able to get access to buildings, to rooms, to floors, to data centers, even as granular as a rack with a lock on it that has access to specific servers. All right? Physical access control means that we're governing who can enter specific spaces, right? Authorization is typically granted based on something you have, smart card, token, a physical key, something you know, like a PIN or a password, or something you are. I would say probably something you have and something you are would be kind of the most common, right? A biometric data would be something you are. And your access points into these spaces, well, those are your doors, and that's what's going to be restricted to individuals that have the appropriate credentials. Spaces could also be subdivided into different zones. For example, I used to own a service provider company, and we did dial-up and T1s and broadband access, and we had a bunch of equipment stored in, or not stored, but functional equipment in a data center, Quest Communications data center. And we had to check in at the security desk to be able to get access to the building. We were only allowed access to a specific floor. And when we wanted to go into the data center, we had a hand geometry scanner on the front door and a PIN that you had to put in. So that was something you know and something you are. And then once you got in, all of the racks, the common racks, the floor was shared by lots of different customers. The racks all had locks on them. Some of the racks were in cages, depending on the organization, and our racks had locks on them. So we had multiple layers of security, right? So that would be considered what we call a high security system. Other high security systems also include things like anti-passback mechanisms, meaning somebody can't reuse credentials to enter again unless they've already exited, right? So I go in, I swipe my badge to get in. So let's say, for example, somebody badges in, right? They swipe their badge to get access to a facility. They can't pass their badge back to somebody else to also get access to that facility because they haven't swiped out, which means essentially, for all intents and purposes, only one person can swipe in and swipe out. That's what they mean by anti-passback mechanisms, all right? Reusing credentials without first exiting, right? We also can employ things like dual custody or dual key entry, meaning that we have to have two separate valid credentials that have to be presented within a specific time window before we can grant access. All right? So physical access control restricts entry to physical spaces with keys, with tokens, with passwords, with biometrics. Could be something you have, something you know, something you are. Your access points are your doors, your gates. The zoned access means that we have spaces that could be segmented so only certain individuals can get into those specific areas, and so on. All right? In a real world scenario, I guess probably a good way of a good evaluation would be like a Cisco ICE integrated environment, right? Cisco Identity Services Engine. So if we're using anti-passback, that means the badge readers, time-based access could be enforced. Dual custody means that we're using multi-factor authentication, and zoned access might mean we're implementing things like 802.1x, device posture assessments, profiling, that kind of thing. Does that make sense? All right. What about the technology? Access control tokens are available in different technological shapes. Yeah, that's okay. I mean, mostly nowadays we're using digital tokens, right? But we used to have physical tokens. They could be a card, it could be a fob. There are biometric examples as well. But why do we mention that? Because access tokens are used to authenticate users at entry points, right? These tokens store the identifying data that gets read by a device, and then it gets sent to the system for evaluation. That token could be swiped, it could be inserted, it could be read via a near-field communication, but the token itself is going to include things like a system identifier, meaning who does it belong to, what architecture or infrastructure does it belong to, and then it would have a unique identifier to identify the individual. All right? That system, when you utilize that token, will evaluate whether access should be granted or not based on the location of the reader, the time or the date, the biometric data, of course, right? The data points that we're using to verify the individual could be fingerprint, could be a retina scan, whatever, or other attributes like a PIN code, voice patterns, and so on. A lot of times biometric readers will actually require you to put in a PIN so that you can index the stored data points. So for example, when I was going into the data center and I had to use the hand geometry scanner, I would put in an ID, which is basically a PIN code, and it would that would then link to the biometric data that's stored in the database, and I would then scan my hand. All right. So access control tokens, physical or digital items that store users' identity data, and then that's going to allow us to interact with the reader. The reader interaction itself means that we can swipe, we can insert, we can scan the token, and then we're going to send that data to a system for verification. And then the token structure is going to be based on all that criteria, right? The validation criteria we talked about, and so on. Okay? All right. Operation of biometric systems are described in a three-step process. First, observation or collection of the data using different sensors. And we talked about that in the previous slide, right? Meaning that we have to collect the information. Does that make sense? So, data collection, meaning capturing the biometric data, could be a fingerprint, retina scan, voice sample, depends on the modality that we're using for the authentication. Template creation, meaning that data has to be now converted into some sort of digital template. And that will vary. How many data points you collect and the template you generate will vary depending on the biometric type. It'll vary depending on the vendor. And then we have to match a template, right? That newly created template that we store gets compared against the templates that we're capturing in real time. And we, of course, will identify, is this a match? Is this not a match? All right. Most of these systems will use something called a statistical threshold to decide whether or not a similarity score is high enough to say this is a match. It's like a threshold of accuracy, right? It's not binary. It's probabilistic. What does that mean? It's not a plus or a minus, right? It's not a 1 or a 0. It's based on the number of data points, right? Matches would obviously trigger access approval. Non-match would mean that you get denied and most likely generate some sort of alert, all right? Advanced biometric solutions could also include elements for detecting liveness. Now, what does that mean? I want to make sure that the sample that I'm collecting comes from a living person, right? It's not a static replica, if you will. Okay? So we do observation, we do template creation, and then we do matching. All right? All right. Physical access control systems, referred to as PACS. You might see that acronym on the exam. Remember, we always have all these acronyms that we have to know for the test as well. A security technology integration application suite to control and manage physical access devices, intrusion detection, video surveillance at DHS HQ facilities in the National Capital Region, primarily the Nebraska Avenue Complex. So what does all that mean? Security technologies. And we're managing and monitoring physical access control at DHS facilities, right? These systems are operated by OCSO, the Office of the Chief Security Officer, specifically in the Physical Security Division. All right. Now, I don't know if you'll need to know this specifically for the test. It was in the knowledge review, so it's in this slide deck. But PACS handles access control and intrusion detection. We use electronic mechanisms to manage entry points, to manage alarms. We also generate automated transactional reports, which means that we're documenting who accesses what, when they access it, where they access it, and so on. PACS is actually segmented into 4 different zones. That gives us granular control and monitoring across different areas. All right. We don't really need to get into the details of that, but the PACS itself, by definition, is just a suite of integrated technologies that manage physical access and intrusion detection. The scope, of course, is DHS facilities and the NCR, specifically the NAC, and we're managing this with DHS Office of the Chief Security Officer under the Physical Control Division. All right? All right. So, you can see that it has an identification component. It has a visitor management component. There's some other pieces as well. We'll talk about the identification piece first. And again, I don't know that I would spend too much time on this in your self-study, right? When you're preparing for the test. First of all, this domain is only 13% of the exam, but I doubt you'll see too much about this. Maybe possibly one question, right? But PACS uses PII, right? Personally identifiable information, and something called a PIV, personal identity verification, cards so that we can authorize access to secure facilities. Obviously, individuals have to be pre-authorized so that their credentials can be created, and then those credentials get read electronically. This would be for visitors, for contractors, for service personnel. But what if I don't have individuals with PIV cards, right? Visitors, contractors probably aren't going to have permanently issued PIV cards. So those individuals are going to have to be vetted and granted access a different way. There's a specific form, 11,000-13, that gets put into the system. We also use that information to run checks against the NCIC, the National Crime Information Center database, looking for criminal records, outstanding warrants, that kind of thing. The information gets stored in packs, but it's not shared across to different divisions, right? There is still this idea that we need to protect this data. Foreign nationals would get processed differently based on the Foreign National Visitor Management System, or FNVMS. Okay? This is kind of a textbook example of physical access control intersecting with identity management and legal compliance, right? PACS uses MAC, mandatory access control, meaning only pre-authorized individuals can enter, and access is going to be tightly regulated. We have different authentication factors, right? Something you have, that would be your PIV card. PII would add elements of something you are, like your identity attributes, your height, your weight, your eye color, your hair color, those kinds of things. All right, visitor vetting, right? This allows us to manually enter information, but it does provide a little bit of administrative control risk, right? Human error or insider threats could be an issue, right? The NCIC integration, that's due diligence, background screening. And then we have data segmentation, which really is implementing least privilege, need to know principles. Does that make sense? All right. Yeah, I don't know why this is covered so much in the knowledge review. Like I said, we're going to cover it because it's in our slide deck here, but I wouldn't, if you're studying for the test, put too much into this one. The parking permit management, the Office of Chief Administration Officer uses PACS to issue and track parking permits for NAC. They use Form 2941. They enter, they manage permit details, your name, your address, your permit number, the issue date, the expiration date. And then we have an alarm monitoring and intrusion detection piece, which is also managed by OCSO. That means that we're going to log all alarm activities, if there's a door that's forced open, if different sensors are triggered. And we have lots of different detection mechanisms in this case, right? Could be sensors, could be lights. But the only PII collected by this suite, if you will, would be first and last name of the individual authorized to arm or disarm a system, and the location of the alarm device or a keypad that was used. Okay? All right. I mean, I guess in a sense, we're talking about mapping physical security controls to compliance and audit readiness. So, as an example, this is a great example of things like least privilege. Only authorized individuals, for example, can arm or disarm, meaning that we're limiting insider abuse. There's an audit trail, right? So we can do forensic analysis and accountability. All right. There's also a component of privacy by design, right? We're collecting a minimal amount of PII. That kind of aligns with FISMA or Privacy Act principles. And then we have access tiers, right? Zones are mapped to different access tiers: executive parking, contractor zones, sensitive areas, public facing areas, and so on. So I guess in that sense, it's not a bad thing to discuss, right? If you can extrapolate these concepts to other areas of physical control. Identification, authentication, authorization. Identification, of course, is the assertion of identity, right? Very sequential process, right? IAA, identification, authentication, authorization. Identification is the act of declaring your identity. It could be a system, it could be an individual, right? Basically, the starting point for access control. Tell us who you are. Now, there's a couple reasons why we might want to have that, right? Number one, it's going to enable traceability in the logs. We're binding identity information to controls and to actions. Okay? Authentication verifies that the identity that you claim is a valid identity, right? And this would be something that you know, like a password or something that confirms your presence, but it establishes a trust between the user and the system. The final step, authorization. Once the identity is confirmed, this system will now determine what resources that user is allowed to access. Identification provides uniqueness. Authentication confirms the validity of that attested identity, and authorization enforces control. All right? So let's say a user logs into a corporate portal using their email. The system might then prompt them for a password and maybe some sort of push notification code or a secondary code like authenticator app code, something like that, right? Based on their role, are they a financial analyst or whatever, they then get granted access to specific folders in SharePoint, or they would not get access to HR information, that kind of thing. All right. Identification badges. The most common form of physical identification and authorization is a badge. It's going to contain the name or the logo of the organization, the name of the badge holder, a picture of the holder, and so on. Right? It's really one of the most commonly used physical access control pieces. It gives us a visual ID and a mechanism for allowing access into secure facilities, right? So again, standard components, yeah, you're going to have the organization's name, company name, logo, whatever it might be. You'll have the holder's name, their photo, right? That gives you that kind of visual identity confirmation. Visitor badges, because they're a little bit more generic, we want to make sure that people understand that that badge is temporary. So usually there's something very unique about those badges, something to uniquely identify them as temporary. But there's also the potential for human error, right? Guards, other individuals don't always look at the badge and say, does this badge match the individual? All right. Now, it does depend on the environment, right? Certainly in high security environments, military installations, government facilities, they're probably going to be a little bit stricter when it comes to that. Access badges also often get embedded with data. So they're not just a plastic card, they actually have a chip on them, or they have a mag stripe or something like that that stores information. And then we swipe the badge or read the badge, that gets validated against a central database, right? The problem with the badge, though, is it's not what we call person bound. What does that mean? That means that they can be shared. Somebody can hand somebody else their badge. Now, again, if you're doing a visual match, then that might be a little bit more difficult if you don't look exactly the same as the other individual. All right. A user ID, pretty straightforward, very common way of identifying individuals that usually are accessing some sort of technical resource, right? Basically giving us a way to uniquely identify individuals. Think of it like a label that gets assigned to an individual. That label is unique to them, so that's going to distinguish them from anybody else that might be in that environment, right? It gives us an entry point for identity, but there is no proof of legitimacy when it comes to a user ID. All right? Also, uniqueness is the key. No two users should have the same user ID. Why? Because that's going to destroy accountability. That's going to destroy auditability. But user IDs are not authenticators. It's just simply a claim of who the user claims to be. We don't trust user IDs. They have to be paired with some sort of authentication factor. Something you know, like a password, something you have, that kind of thing. All right? That's how we verify authenticity. But once they're verified, then we can enforce authorization based on policies. All right? So if we're looking at AWS IAM as an example, the IAM username or federated identity would be your user ID. That would be used for things like SSO or whatever. The authentication is your access key or your password. Could be a STS token or multi-factor authentication. And then the authorization is the IAM policy that gets attached to your user identity. In Active Directory, it could just be a user ID. The system will prompt you for a password, maybe smart card authentication, and then your group membership will determine what you can access and what you're authorized to do. That makes sense? An account number provides unique identity for a particular user within a system or enterprise. We enter account numbers as part of financial services applications or transactions. A PIN provides authentication information needed to determine whether the user has legitimate rights to use the account number and access information. Yeah, I mean, this is pretty obvious, right? The account number uniquely identifies a user to the specific system, typically tied to some sort of financial or enterprise level service, but the account number itself is not enough, right? Account number is almost just like a locator, right? What account is being accessed? It's the PIN or whatever other authentication factor that verifies that the user has the right to access the account. This is what we call a two-part access mechanism. One for identification, one for authentication. Pretty straightforward. A MAC address, media access control address. You might say, well, wait a minute, that's a layer 2 address that identifies a host in an Ethernet network. But guess what? It can be used as an ID. If we're running 802.1x, extensible authentication, and the device, the supplicant doesn't support an 802.1x client, and we don't want to use like a web authentication feature, we might use something called MAC authentication bypass, where we use a 48-bit hexadecimal ID, the MAC address, to identify that individual. Not the individual, but the hardware, right? MAC addresses are burned in. Now, they can be modified in software, but MAC addresses also have another property. They're globally unique. All right? Historically, they were used to identify and authenticate devices with high confidence. I would say, for the most part, that's not the case, right? Because MAC addresses can be spoofed, or they can be changed in software. They're not always considered the best authentication method, but it's better than nothing, right? So MAC addresses aren't considered strong forms of ID, especially in a secure environment, but they can still be used for things like DHCP reservations, filtering on a wireless network, and so on. And we can implement things like dynamic ARP inspection, other protection mechanisms to protect against ARP spoofing attacks or MAC-based attacks. All right? In a zero trust architecture, we're probably not going to rely on the MAC address alone, but in some cases we have to, because that's all we have to go on. If it's a security camera, if it's a printer, or something like that. Does that make sense? All right. IP address, a little bit different. IP addresses can identify your location. We can tie IP addresses to location, but IP addresses are logical, right? They're not physical. They're temporal. They will change depending on where you're connected. The MAC address identifies the physical hardware. The only way we could use maybe an IP address in terms of security is your location. But even that can't be entirely trusted. I could launch a VPN, connect to a completely different location, tunnel all my traffic back to that location, and I would then appear to be from that particular location. We know that based on domain 4, right, IPs are organized into subnets that allows us to group devices together, and so on. I would say same thing here. IP addresses can be spoofed. They're not really strong indicators of identity, right? But they can be used as a data point. We don't use them by themselves, but we can use them as a data point for other functions like maybe geofencing or identifying through security intelligence known malicious actors based on the IP address information, that kind of thing. Okay, we're almost done with this domain. We'll try to finish it within the hour here. Not this domain, this section of the domain, I should say. RFID, radio frequency ID. All right. Non-contact technology used to identify, track, and detect objects using radio waves or radio frequencies. Doesn't use a barcode, doesn't use a magnetic stripe. It doesn't require direct contact or line of sight. Hey, that rhymed. All right. So what does an RFID system typically contain? We have a mod-demod technology, modulation and demodulation technology. That's going to convert the radio signals into usable data, or vice versa. We have an antenna which allows us to transmit and receive those signals between the reader and the tag. We have the tag itself, which is just a small device that stores limited data and can perform basic processing. And we also have chipless RFID, right? That's what we call RF fibers. This is going to use material that reflects part of the reader's signal back in a unique pattern. So you don't actually have an integrated circuit. Those reflected signals become a signature. And then we use that signature to identify that object or that person. All right? All right. Now, we're going to break down a little bit more about RFID. I don't think on the exam you're going to need to know the technology, right? They're not going to ask you specific questions like what frequency range does it operate on, what it is in the ISM bands. But again, they probably won't ask you that. Now, you might have to know about different types of RFID tags, like active tags or passive tags, and I think we'll see that here in a couple of minutes. All right. So again, 3 core elements. We've got the transponder. Remember, the transponder stores the ID tied to the object, right? That's essentially the tag. All right. The reader, which is your transceiver, that's going to be what sends the radio signals to power the tag, if it's a passive tag, and read or write data to that particular tag. And then we have the backend database that stores all of the information, right? The data that's associated to the tag itself. So how it works is the reader emits a low-level magnetic field. That field actually provides energy to the tag if it's a passive tag. Now, you can have tags with batteries. They're not as common because obviously those batteries have a shelf life, right? The tag responds by this emanation by transmitting its ID over the radio frequencies, right? The reader reads that information, decodes that signal, passes it to a local application through some sort of middleware application. That middleware acts as like a bridge between the reader and the actual RFID system. And then the last step, we match the tag ID with the records that are stored in the backend database, and we're able to provide access control. So an RFID badge gets scanned at the door, the reader energizes the tag, the ID gets sent to middleware, the access is granted if we have a match in the backend database. We can also use RFID tags for retail inventory, right? The RFID reader scans the shelf. The tags respond, and we update stock levels in real time. We can use it for cloud security as well. All right? So lots and lots of different options with these RFID tags. What are some vulnerabilities? This is more likely what you're going to see on the exam, right? Being that it is a security exam, you're going to have to know what the vulnerabilities are for these RFID tags. RFID tags are often referred to as dumb devices, meaning they'll respond to any signal. It doesn't matter who's sending the signal, all right? But what does that mean? Now we have lots of risks with those tags, right? Eavesdropping or skimming. An attacker could actually intercept the radio signals up to, I don't know, feet, maybe meters away, using just a standard receiver. And then if you don't have any encryption controls, you can impersonate a reader and then you can get the data from the tag. Even if the tag contents are actually protected, you might be able to recognize patterns of different tag activity that can indicate movement, behavior, specific transactions taking place, and more importantly, denial of service, right? We can flood the system with rogue information. We can jam frequencies. There's also a concern for privacy, right? Aggregated tag data can expose things like personal habits, social interactions, financial behavior. We might even be able to read private information from the tag just by being near that individual. So we have to be concerned about eavesdropping, spoofing, traffic analysis, denial of service, and privacy abuse. All right. Spoofing. Based on data collected from eavesdropping or traffic analysis, it is possible to perform tag spoofing. Packages like RF dump runs on a notebook, a laptop, which allows users to perform reading or writing tasks on most standard smart tags if they're not protected. Meaning the attacker can use data that they gather from eavesdropping or traffic analysis to generate their own fake RFID tags. All right. We can also do data overwrite, meaning we can inject bogus data into the existing tags. And that might influence a system into granting access, possibly misidentifying assets, also denial of service. With high-powered RF transmitters, we could jam legitimate signals. And insider threats is a consideration as well, right? Internal personnel, if they have access to the RFID infrastructure, could introduce a lot of malicious tags, or they could disrupt operations that way as well. Does that make sense? All right. Okay. RFID reader integrity. RFID readers get installed in locations without adequate physical protection. Right? I mean, think about it. You're paying, do tap to pay or whatever, or you're in a store and you're checking out. It's not like the reader is in a secure location. It's typically right on the counter, right? So if a reader's placed in an insecure location, it could be physically tampered with, right? Going to a gas station, they could have skimmers and stuff like that. You could have hidden readers to intercept your tag data. That means that you have privacy breaches if you don't have compensating controls in place, right? If you don't have firewalls, and I'm not talking about physical firewalls, I'm talking about logical firewalls or intentional protection mechanisms, you could have issues, right? RFID malware does exist, right? Viruses can show RFIDs could possibly carry payloads that can be delivered. And then there's also personal privacy concerns. Item level tagging in a retail environment kind of raises like ethical or cultural concerns as well. Even if, especially if the tags remain active. I was watching a video online the other day, and it was about shoplifting, and the police were tracking some individuals that went into a Gap and stole a bunch of jeans. Like, they just picked them up, walked out, right? Well, apparently now, of course, they had sensors on them, which most typical retail people will use. But apparently now they put trackers in their products. And the police were literally tracking these individuals because they didn't know that there was a tracker, like an Apple tag or something like that. It wasn't an Apple tag, but something like that. And they were able to actually track down where these individuals were. And they had a device that they got from the retailer where they could actually activate an alarm on the tracker. So when they got to the place, and of course the individual's like, we didn't do that, we didn't steal that. They push the button and the alarm starts going off, and well, guess what? Now they're caught red-handed. I thought that was pretty awesome. Pretty cool concept, right? So There are some privacy concerns. Signal proximity is a concern as well, because the tag has to be within range. All right. But that also means that it can be read as long as you're in range. There are operational benefits, which is why they're used so often, to streamline things like inventory management, so that we can reduce tracking costs and so on. All right. So that concludes this section of this domain. We'll wrap up this video and we'll get into the next video. We'll see you there.